Hello friends, today we discuss another important topics for graduate students. The topic is homomorphism of groups. Now, first of all, into homomorphism. The meaning of into and the homomorphism. So first of all, recall about only homomorphism. A mapping F from a group G with their binary operation into another group G days with their binary operation is homomorphism of Z into G days if the mapping over A operations B of the first group should be is equal to FA. FA is the member of G days and FB is the member of also G days. So FA operation B will be is equal to FA binary operation, this operation for G days, and FB. And recall, for all AB is the member of G. So this is the definition of homomorphism of groups. Now in the diagram, A, this is B, their operations by means of closure property, A operation B. So this is FA, this will be FB, and here is the function of A operated function of B. So the functions will be same, that is FA operation P will be is equal to FA operation FB. Now here the meaning of into. Suppose there is a member D which doesn't have any preimage, then we know that it is the into mapping, or now by means of homomorphism, so the mapping is known as into homomorphism. Now what is onto homomorphism? When the mapping from Z onto G days is known as onto homomorphism. That is, all members of G days, there exists at least one preimage in G is known as the term onto. So you should quote it this letter onto, and here is should quote it into. This is into and this is onto mapping. Now let us take a very important example. Suppose a group R plus, this is the additive group of real numbers, and now C multiplications, operation is multiplication, the set of those complex number whose absolute values is 1, whose absolute values will be 1. Now let us define a function real number to complex number as fx maps e raised to ix. Okay, e raised to ix means cos x plus I sin x. And now it is the complex number whose absolute values is 1. So when we taking the mode of fx, that means under root cos square x plus sin square x will be under root 1, that is 1. Now for checking about homomorphism, so let us take any 2 points, any 2 members of the real number. X and y is the member of R. By closure property, x plus y is also the member of R. Now function x plus y, because we are going to check about homomorphism, A operation B. Now A plus B or x plus y will be e raised to I. When fx is e raised to ix, then fx plus y will be e raised to ix plus y. So e raised to ix multiplications e raised to iy by exponent rule. So what is the e raised to ix? It will be fx multiplication, this will be fy. And now you should remember here, this is the operation which is multiplication, and this operations for the another group complex number, and here is operation of plus, and this is the operation for R plus, this is the operation. So both operations will preserve their own groups, not other groups. Now, so this is the first conclusion. Now, if we take any e raised to ix is the member of complex number, then there must exist and x is the member of real number such that when f maps the point x goes to e raised to ix. So that means we want to say that for any arbitrary element of the complex number, there must exist or at least one member of real number which maps e raised to ix. So no member of the complex set will remains unused. So this is the onto functions, and the function is